So I'm not sure where everyone's at with how much they've used AWS or IonQ or maybe any other platform. So what I did is I created this deck where we'll just quickly go over some of the basic things to be aware of. And this deck is available. I uploaded it on my GitHub. So if you want to take that down, and I can also post it in the chat at some point as well. Let me see if I can find. So yeah, I can post that later on, but you can also download this presentation from GitHub. And then I thought I'd go over some code examples, depending on if someone wants to get that deep into it. So you can actually see what steps are needed to run something on IonQ. I think it's pretty amazing. I've been just thinking about it. It's pretty amazing that we can actually do computation with ions, with basically atoms, charged atoms. So I think that's just fabulous. Okay. So this will just kind of go over just some of the basics. So after you get into AWS, you will need to find, of course, you're going to sign in. And I've got some links down here for the AWS Bracket service and how to get started. A lot of the instructions are over there. What you would do is you'd have to do a search. Once you get into the AWS Management Console, you do a search for Bracket, and then it comes up with this screen over here, and then you click on this Get Started. All right. Now, it has to set up AWS Bracket on your AWS account. So there's a video over here that kind of goes over the steps to get going. So I'm not going to run that, but just to let you know that this video over here is there. And there are some other introductory videos that will be available when you get into this getting started screen. Now, after AWS is set up, what you're going to have is the way it sets it up is going to allocate an S3 instance, or this is a storage instance, and it will, during the setup process, is going to set up a bucket. And so this is like a file folder. If you think about your drive and a file in your drive, basically Amazon sets up a drive, and that's a storage location where your results will go. In the setup process, it'll basically say it's going to set up an S3 bucket. It'll probably give you a default name. This name over here, I changed it, so this is not the default. And then you can create a directory, and I think there's a default directory it sets up. So, but the important thing to note is that you will get an S3 instance, will have a name, and it'll have a directory inside it. You're going to need the name of this S3 instance and the name of the folder when you go to the code, because you have to enter those two things in the code. So there's just something to be, aware of. And please ask me any questions. I mean, it's a very short, small group, so happy to answer any questions. In addition, when you do the AWS setup, it also creates an Amazon Sage Maker instance. And what it does is within Amazon SageMaker, it creates an instance for notebooks. So like the Jupyter notebooks. So you will see that appear. And initially, of course, it'll probably be stopped. So then you have to click on it, select it, and then go to actions and start that instance. So this is basically, as you've done maybe programming in other locations, where you open up an instance of the Jupyter Notebooks kernel. It comes up, then you can open up different Jupyter Notebook files. And if, for example, when you are in IBM Quantum, they already have a Jupyter Lab instance. You're already inside it. So this is basically setting up and starting Jupyter. Now, keep in mind that when this is running, you are paying for the service. So this is Amazon Web Services. When you have an instance of Jupyter Notebooks running, see right now this is stopped. When it's running, you are paying for it. So it is important to make sure that when you're done with it, to turn it off. All right. So when you go into the Amazon Bracket service itself, so you can easily just, most of these places are easy to get to by clicking on the top left AWS symbol, and then it shows you all the recently visited services. And if you just set up Amazon Bracket, you'll see Amazon Bracket over there. If you don't see the ones that I've got over here, like S3 or SageMaker or Billing, you can just type it in there. And when you type it in there and go there, it'll show up in your recently visited. So your list might not look like this, but it just depends on what where you go. All right, so you would find Amazon Bracket, click on it, and then it'll open this up. So this is the main screen that you would see once Amazon Bracket is running. There are these 4 tabs: devices, notebooks, tasks, and announcements. So it'll start out, I think, in devices, and so you see the devices that are available. And of course, you can go to D-Wave. You have both the 2000Q and Advantage. You've got IonQ as a device that's available. And then you've got Rigetti, and you've got Amazon's simulator as well. Now you can click on these, and it'll give you more information about those devices. Okay. All right, I'll put this over here. Oh, okay, there's a question on how does Amazon charge for this. So if you go, okay, so there's a charge for any service in Amazon. Storage has a charge. If you run, like Elastic Compute or EC2, that has a charge. If you set up any web services, that has a charge. So in this case, the two, I would say there's 3 main charges. The charge for the S3, which is the storage, is minimal. I haven't paid anything for it. I've had this for a few months. I've not had any charge from that. So I think unless you reach some certain amount of volume, I think the charge for just storage is very little. There is a charge for running the Jupyter Notebook, and I think I was paying probably a few dollars for maybe a week. So it might add up. I mean, if you keep your Jupyter Notebook running all the time, day and night, after a month, you might end up paying a few, $10, $20 or something like that. The next charge is to actually use the devices. So when you click on this, one of the IonQ or D-Wave, it will tell you the charge. And let me see. Okay, so assuming that you've clicked on IonQ, it will open up a separate window, which I haven't shown over here, but it gives a little bit of a description of IonQ. It gives, the picture of what the ion trap is, how it's represented in a graph model. And, the key thing to take away from this is if you were to go to Rigetti or IBM and you look at their QPU, their quantum processing unit, most of those are not fully connected qubits. You see something like a T shape or a plus shape or a square shape, and there would be a few connections, 3 to 4 connections between one qubit and the next qubit. In the case of the ion trap, there's 11 ions over here, and every ion is connected to every other. So it's quite impressive. Again, these ions are actually floating in a vacuum inside a magnetic field. So they're like trapped in a magnetic field, and they're like literally floating in there. But through the way they use lasers, they are able to, they move the ions and they move them into higher energy levels. But there's a mechanism in which they're able to entangle them where they are connected with each other. So depending on the gate operation, you can connect any ion to any other ion. Now here's the cost for running it. You pay 30 cents every time you submit a task to the actual hardware, the actual quantum processing unit, and then you pay 1 cent per shot. So in a lot of the examples, there are 1,000 shots. So that's $10 right away. I would suggest that don't run any example on the QPU without reducing the number of shots down to maybe 100 or 10. I've been using 100, where you pay $1 plus 30 cents. So all right, so and then it's available, I believe, from around 8 a.m. Eastern time to 4 p.m. Eastern time. When I submit some jobs, it takes a few hours to actually execute. And then in the evening, it's down. So I don't know if they are doing maintenance every day or if they are, allocating time to other services. So, but it's only available during this time period. Okay, so to get started, assuming you've got Braket set up, you would then you looked at the devices, you would then go to the notebooks tab over here, or link, and then you would see Amazon sets up an instance. You could call it like a sample instance of a notebook instance. So you would click on that and then start it. It then opens up Braket notebooks over here, and then you'll see the Jupyter Notebooks instance start, and then there will be a Braket examples, which will contain some folders, and then there's a lot of good sample code in there that you can use. And you would start out with simple circuits and then look for the starter code in there, which starts out with just the syntax of the code, the gates that are allowed, and it will run it on the simulator, and then eventually you can go to the more advanced examples where you actually run it on the quantum processing unit. And you can pick Rigetti or IonQ. And if you set up your problem for optimization, then you can run it on the D-Wave. So again, D-Wave is different. Question, can I cap my cost if I accidentally type in 1 million shots? I don't think you can. I think once it's gone, you're going to get charged. So be careful. Let me just go to the next one over here. Okay, somewhere in my presentation, I do show what the billing screen looks like. Within the billing screen, there are options for monitoring your costs and getting notifications if you've gone above a certain number. So if you put your notification on like $10 or $100 and suddenly you get a bill for $1,000, I think you've already signed that you're going to pay whatever they charge you. So I would be careful. Okay, so we already went through the notebooks link, and now I'm going to go over the tasks. The tasks over here shows when you submit a job to one of the devices, your task IDs will show up. It'll say whether it's completed or queued. It'll tell you what device you're running it on. What I have found is none of the jobs come back really quickly, like, within a few seconds. They take, sometimes they take hours. So you run your code and then you basically have to stop after you submit your job. And there's a snippet of code that you'll see that you can run to retrieve the results of a job. So you have to click on your task ID, right, depending on the job that you had submitted. Go over here and then copy, this is what I've been doing, is copy this ARN code, the quantum task ARN code, and copy paste that into the code and say, okay, what are the results? Now this is actually a file. This generates a file that's going to sit in the S3 instance. So we used the Jupyter Notebook to execute the code. It was executed on a device, one of the devices. When you execute the code, it shows up in the task list that this is something that's being executed. After it's complete, you have a task ID to look at the results from the code, but the actual results are also sitting in your folder in your S3 instance. So you can go to your S3 instance and you can find the actual file that has the JSON file that has the results in it. But you can also take the task ID, put it in the code, and have it retrieve the results. Okay, and then the last one here is announcements. So they do have announcements on new devices or devices that are removed and maintenance. So it's good to track that as well, because you might submit a job or you might be thinking today is the day I'm going to actually run everything. And then you find out that nothing is running. So it's good to check the announcements. Okay, so getting started with the code as this is a really bad image, but so I apologize. But I had mentioned that you need the S3 bucket name and you need the S3 bucket folder. And so you'll see when I go through the code example where those two things go in. But once you've got that, you're good to go. All right. So depending on how we're doing on time, I was thinking of going through two examples in the code. The first one is the Bernstein-Vazirani algorithm, which is a very simple, it's the basic algorithm in quantum computing. You have a set of Hadamards, you put some C-NOT gates, put some more header marks, and then you measure results. And what this algorithm does is, depending on where your control, where this dot is on your C naught, those values are 1, and where you don't have the C naught, those values are 0. So when you build a circuit and then you measure, wherever you have this the dot, you should get a 1, and where you don't, you get a 0. And of course, if you didn't have header marks, you're not going to see any values. So I thought this is a very simple algorithm. I wanted to try it out, so I put it on IBM Q, and then I put it, then I tried it out on the IonQ. So one of the reasons for doing that is whether it's Rigetti or IBM, when you're not using the simulator, when you actually use the quantum processing unit, one of their devices, there are errors in the qubits. The qubits decohere, they lose the information. They're not very accurate. And then even a simple algorithm like this, when you look at the results, you don't get a perfect, like in this case, you should get a 0, 0, 1, 1. You don't get 100% or 100, if you put 100 shots, you don't get 100% of 0, 0, 1, 1. You'll get all kinds of different values. And so what I wanted to do was kind of compare what you would see on IBM on some of their devices, and then see what you get on the ion trap. Because with the ion trap, you have, number one, you have all the qubits are connected, and then there's less error. Now, what with the ion traps, the gate operations take a little longer. I mean, you won't, we won't detect the delay, but compared to superconducting qubits, the ion trap, the qubits in the ion trap are slightly slower, but they have less error. So for example, when you do a CNOT gate between qubit 0 and qubit 4, if those two qubits are not really connected on a chip, on a quantum chip, then the quantum processor will do a bunch of swap operations to bring that information to, because it can't really connect Q0 to Q4, it's going to do some swaps to bring that state to a place where it can actually do the calculation. Now with the IonQ, since every qubit is connected with every other qubit, this circuit should not need any swaps, right? It just should be connected. So anyway, that was one example I thought I would try out. And then the next example, so here's an example of what the quantum hardware looks like. So with IBM Q Athens, you have qubit 0 and 1 connected, 1 and 2 are connected, 2 and 3 are connected, 3 and 4 are connected. But if I do a C0 gate between 0 and 4, there's no direct connection. So it's going to do a swap gate and bring the state from 4 to 1 so that it can actually do the C0. And so there's a lot of extra gate operations that happen on one of these chips. So the second, if you get to it, is a very simple example. There's a gate called a Toffoli gate. It's that one was a controlled NOT. This is a control NOT. So there's basically two controls. So it's very simple. If basically it's saying is, if I have a one state on both of my controls, then I will flip the state over here. So if this was a 0 state, it will become a 1. If it was a 1, it will become a 0. Only if I've got 1 on both of the controls. Now, it looks like a simple gate, and it's, used a lot. However, this gate requires all of these smaller gates or like basic gates to actually implement. And so on any of the IBM devices, if you put a Toffoli gate, you're using up a lot of the time and you begin to lose the coherence of the qubits. So this was just one simple gate. We can see how it behaves on the IonQ device. So here's just an example of if you have an IBM circuit, you put two Hadamards, you put a Toffoli gate, then it's going to go through a bunch of transpile, basically converting this into the actual gate operations that the quantum processor will do. So it will go from here. You'll see this screen flash, which is a bunch of different operations. And then eventually it shows you this is the final result that it decided to do because of, this total gate that I wanted or circuit that I wanted. So, all right. And then finally, for billing, if you do a search for billing, you'll see that. And the billing section will show you some, costs. It'll give you basically the categories in which the costs are coming from. So like, for example, in my case, I spent $2 on Bracket. I think this is for this month. Last month, I spent $10. This month is $3. And then it's anticipating like $8 for next month. And so Sage Maker is the Jupyter notebook instance. So it's $1.30 for that. And then Bracket is the actual QPU time when I submit a job to a quantum processor. Okay, I've got some information here on getting started with running a Jupyter notebook locally, not in the Jupyter notebook instance that's in Amazon Bracket. But there's a lot of steps involved there. You have to read up on some of the SDK and how to control your, how to get your account set up on a Jupyter file in a local instance. But anyway, I put some links over here for that. Okay. All right, any questions?
Yeah, Alex, so if you were knowing what you know now, would you, and all things being equal, I guess, would you use the IonQ or would you use the IBM Q?
I've been using IBM Q. It's a great environment. It's easy to get started on. The simulator allows you to go up to 30 qubits or 32 qubits. And it's very convenient. I mean, it's great. IBM Q is a very well put together environment to get started. And as we've taught students, you've got the circuit designer and then you've got the Jupyter lab, and it's easy to run local instances. So, and it's available. So it's a great environment. Now we do know that whenever we've tried running our circuits on an actual device, super conducting qubits, we don't get the best results. But that's where you have to learn about error correction and all of those things. And hopefully, as the chips become better, you'll see we'll see less errors. But within a few gates, even in the one Toffoli gate, you begin to see a lot of decoherence. So it's going to be a while before we get good results. The thing with the IonQ is I'm going to open up the code now. You'll see that the results are dramatically better. I mean, the results are clean. And so even though the AWS environment has all of these different pieces that one has to figure out to just get started, I think that it is worth running your circuit if you're learning about these on the ion trap, because it's 11 ions, it's 11 qubits, they're fully connected, and they give better results. So now, of course, most of the work can be done on a simulator, right? So I mean, if you're learning and you're trying out different circuits, you don't really need to submit that to a real quantum processor. So
there's nothing, nothing show-stopping about the IonQ that says, hey, folks, don't go there.
No,
I mean, you've got the bias towards what we're familiar with. Most of us, I think, are familiar with IonQ. I'm sorry, with IBM Q.
Yeah.
IonQ is probably a new experience for almost all of us.
Yeah, I think,
so you have a bias.
We're doing this presentation and, this was Terrell's idea to do this presentation. So there's a little bit of a hurdle to get set up in Amazon and get all of these instances going to try it out. But I think it is worth trying it out.
There's a question. Go ahead.
Also, I mean, the service is not available 24 hours a day. It's only available for a certain amount of time. And I don't know, it's probably very busy. So like I said, that my jobs take hours to actually complete.
It takes you back to the good old days in the 70s. Besides, for me anyway, personally, I'm not up late at night like I was when I was in my 20s. So that's not a showstopper. Tomas has a question, and I think the answer would be easy. Have you had a chance to use Azure Quantum?
I have used Azure Quantum. I'm actually in the early access group. You can use Azure Quantum using Q#, like Terrell, you were teaching about Q# in the course. Which requires a lot of setup for the, I think you have to set up the whole Q# environment or the Microsoft development environment and then do coding in Q#. I bypassed all that and just installed the Jupyter SDK or the Python SDK for Azure Quantum. And so I can just use my notebooks and access that. So that was a little easier. And now again, they don't have real hardware. I mean, they're still developing the hardware. So.
Okay. Raja asked a question. Why are QC manufacturers offering their hardware through Amazon or Microsoft rather than directly?
So they are available direct. Like, for example, D-Wave. D-Wave is available direct, and Rigetti was available direct. I think that, so I don't know the strategic reason for, why they have started putting these services on AWS. My thought would be that this allows the manufacturers of the quantum processors to focus on the quantum processor and not worry about all of the extra, the software stack and connectivity and all of the billing and all of that stuff that's needed to get, a mass of users coming in and accessing the device. I mean, they want to focus on making the device better. And I think that, their energy is best spent making those devices better. So I think, that would be probably one reason why it's great that these services are becoming available on Microsoft Azure Quantum or AWS. Same thing with Honeywell, right? Honeywell is going to be available in Microsoft and I'm not sure if it's going to be available in AWS. At least I don't see it yet. But I think that does allow them to focus on the quantum side. And the other reason is a lot of companies are already in AWS. They already are using either Azure Quantum or they're using AWS. So if these companies are going to take some of their math or calculations that they're doing in those environments already, then these services make it very easy for them to pass data back and forth. So for example, if you're doing machine learning, kind of an example, you have data in S3 and you've got EC2 instances running and you've got Lambda services, then you can easily decide some portion of the Lambda service is going to be pushed to the quantum processor, executed on the quantum processor, bring the results back, and you're all in one environment in AWS.
Yeah, the partnership there with AWS and or Azure certainly adds value for everybody in the ecosystem, frankly. Even the vendors themselves, they don't have to deal with one-off customers, et cetera.
Yeah.
Or this big client base. Another question coming from Doug. What programming language do you use to program in the IonQ? Is it Amazon's own programming language?
I'm
blah,
going
blah,
to
blah.
start sharing that. It's basically Python. You use Python, and they have their they have their own way of assembling the circuit. It's slightly different from the way IBM does it, but it's not that difficult to figure out.
So you'd probably have to use a different library in the IonQ version versus
right. So if you had your local instance on Python, you would do pip install of AWS Bracket, and once you've got that, it's basically you're still using Python code.
So you're using an AWS Bracket library, which communicates to the various servers.
Right.
So you could take an IonQ chunk of code in IonQ, just toggle some switches and have that run on the IBM, at least in theory.
Yes, actually, if you have multiple SDKs already loaded, you would import the Bracket service. You'd import IBM Q, and you could use the same Jupyter instance, same Jupyter local version, and submit a job to Amazon, and then submit a job to IBM. Or submit the same circuit. I think you have to obviously create the circuit twice. You'll have to create the circuit for IBM Q, and you'll have to create the circuit separately for IonQ, because I think the code of assembling the circuit looks different to me. And
there's like QCware. We had QCware a couple of weeks ago, and basically they have a layer around that. So you would literally, if it was all dialed in, you would literally run in the same code from the programmers or the developers perspective. And
I've looked at QCware as well, and QCware actually is more similar to AWS. How you assemble the circuit.
Yeah. And D-Wave, of course, would be a completely different animal.
And D-Wave, right, that's totally different, because there you're trying to do optimization, and you're not creating a quantum circuit.
Konstantinos asks, are there any Chinese quantum computers available?
It's a good question, but I don't think I know if they're available.
Alibaba.
Yeah, I don't know if they're available online, though. Are they?
Yeah. Yeah. I haven't personally touched it, but yeah, you can get to an Alibaba machine. I don't know about the documentation. I personally haven't done that, but I do know people who have, and I don't know if the documentation is in English or Chinese, but more than likely it's in English to some degree, but I don't know. I haven't touched it personally. Something to dig into. Another one from Barry. Hey, Barry. Can Barry access the API with languages other than Python? I guess the AWS world.
So sorry, can you access the
services other than through Python?
Can you access the services other than Python? So that's, I'm not sure because the SDKs are for Python.
Python. I would ask you, Barry.
I've not seen like a C SDK or something,
Yeah.
SDK for something, Java or something.
Probably overkill at this stage of the game. Okay. Right. I think that's it on the questions. Let me just double check.
Good questions.
Yeah.
All right.
Yep.
So basically what I did is, I went to notebooks. I started I clicked on this radio button, went to action, started the service. It takes a few minutes to start up, so I did that in advance. And then when it's running, you click on the URL, and then it opens up this bracket examples. And so you have those directories. Now, keep in mind, when you shut down the service, you lose anything that you might have created or saved. So if you made some modifications, you're going to lose those modifications if you shut down the service and then start the service again. When you start the service again, you get the default examples. So what I've been doing is, any code that I'm writing, I download it to my local drive, right? I basically download it and save it. And so in order to do this demo, I'm uploading it. So I went to upload. I clicked on the example. I've got to upload it. So now it's going to go from my computer, my laptop, to the Bracket notebook instance. As long as I've got the Jupyter notebook instance running, the code is going to stay there. Any changes I make will stay there. But if I was to shut down the service, stop the service, and then restart it, it ends up wiping everything out and putting in the default. So you would just have, so if I made some changes over here, right? So like version 2, make some changes over here, I would just do file, download as notebook. And then make sure I've got that copy for later. Okay, so as I said, this is basically a Python Jupyter notebook. You would do your normal imports. Here you're importing the brackets from bracket circuits. You're importing the circuit, gate, and various other functions. This is the most complicated part of getting started. In the Jupyter, in the examples, you're going to have either an example where you're going to use your account, and it will have some code in here that if you created the default version of the S3 instance with the account, with your account number, then there's going to be code in the examples which will pull your account number, put the account number in here, and use the default folder. So this is the folder. And then this is the S3 instance name. If you followed all the defaults, the examples generally work. But if they don't work, as I have already put down, you basically copy paste the S3 instance name over here, whatever you ended up calling it. But you have to start out with Amazon Bracket. So Amazon Bracket and then something else after that. And then depending on what folder name you created, you put the folder name in there. So, so let's just run it, I guess. I think this is the most complicated part of this, is making sure your notebook works with your account. All right, so I'll run this. So basically, I've got those two values, and as long as those two values are correct, then this will work. All right, so the next step over here, by the way, there's really good examples. They start out easy and then they get more complicated, but I've just put together some very simple steps to kind of go through this demo. All right. So the other thing I'm doing here is I pulled this code out that shows you which gates are allowed. So it basically looks at, so there's two gate sets over here. One is the regular SDK gate set. That's this one. And then it says, okay, for this device, which is IonQ, which gates can I use? So you run that. So here are the gates that you can run on IonQ. So they're the standard ones, X, Y, Z, RX, RY, RZ, right? These are the rotations around the X-axis, rotation around the Y-axis, Z-axis. H is the Hadamard, the C0. S and SI, which is the inverse of S, are the rotations around the Z-axis. They're smaller rotations. T is also rotation around the Z-axis. V and VI, I'm not sure what they are. And then you've got XX, YY, ZZ, which I'm thinking these are the uppercase XX, YY rotations or gates, but I haven't used those. And then there's a swap and then the identity. I don't think the Toffoli gate is in here. I don't see, unless the V is a Toffoli. And by the way, there's documentation that goes over all the gates and everything. All right, so first we'll just use the local simulator. Here's the diagram for the Bernstein-Vazirani algorithm that I pulled from the IBM when I created it over there. I pulled the CHASM code from IBM, just to see what what gates I would need. And here's the circuit. So this is the most, I guess, complicated part of putting a circuit together. You have to start with circuit function, and then you append basically in sequence all the gates. So in this case, we have Hadamards from 0 for the first 4 gates. So H in range 4, that's your first set over there. Then you have an X gate over here. This is, the plus is actually an X or a naught. So there's your X on the 4th qubit, 0, 1, 2, 3, 4, okay? X4. Then you have an H on 4. Then you have a C naught between 0 and 4. Then you have another C naught between 1 and 4. And then you have Hadamards going 4 Hadamards basically. So they will go from 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3. So that. And then you can print that circuit, PV. And so you can kind of compare and see that, hey, it looks about the same. All right, it's not as clean and nice as you can see in IBM, but once you're familiar with this is very readable actually. All right, so let's see. So did I run that? All right, so I've got my circuit. The circuit is in BV, right? Now I'm going to pick my device, which is the local simulator. I'm going to run BV. This is only the simulator. I think the simulator has no cost. So 1,000 shots is fine. And then you'll have the results right away. By the way, what should I get in this circuit? As I said, you would get 0, 0, 1, 1 in this case. When what I notice is that in AWS, the way the circuits work is rather than the numbers going from the bottom up, like 0, 0, 1, 1 is what I'm used to from IBM. Here it's from the top down. So this would be 1, 1, 0, 0. And so you see these results, 1, 1, 0, 0, 0. And the way this circuit works is you have to ignore the last qubit, which is the ancilla qubit. As you can notice, I didn't even put a measurement gate on the last qubit, but here it's just going right through, and it's also giving me the result for the last qubit. So I'm just, if you ignore the last qubit, which is the 0 or the 1 over here, you basically get 100% with 1, 1, 0, 0. So that's the result I should be getting. I should be getting 1, 1, 0, 0, 100% of the time, ignoring that last qubit, which is the ancilla qubit. Okay, so that I ran that, run this. This is just plotting the results. Again, I'm interpreting that I'm ignoring the last digit, the 0, the 1 and 0 over here. So I'm adding them up for me. So it's 100% 1, 1, 0, 0. So then I run it through the IonQ device, right? So I'm now saying, okay, I want the device IonQ. And these names, when you go to the devices, you can copy paste these names out of there. Run. Okay, so here we're saying I want to run the circuit, the Bernstein-Vazirani circuit. I want the results to go in the S3 folder. I'm putting in only 10 shots. 10 shots is $1. No, actually, no, 10 shots is 10 cents. 100 shots would be $1 and 1,000 shots would be $10. So I don't think, yeah, you have to be careful with the examples. In the examples, they have 1,000 shots in there. And so you run the example and you pay $10. There goes your meal. And then the polling time is basically how long it's going to wait for results to come back. But I don't think that's really important because you can always go back and get your results. Okay, so if I run this circuit over here, it's going to create a task. I mean, I'll run it, but I doubt if the results will come back. And then this task ID is already in memory. So if I run this, it'll say that the task is queued. And if I go back to my AWS instance, I'll see that the task is queued. Now, what I've started doing is it's good to also just print out my task. I think it's the task ID over here. Yep. So, this is the task ID. I'm finding it easy to just print it out because later on when I want to go and run it again, which could be hours from now, I have the task ID stored because now when I run the next one, it'll have another task ID. So it's good to just print out your task ID, keep it there so you can copy paste it when you want to recover. You can also go back to the task list and copy it from there, right? Okay, so now in the sample code, it shows how to recover a task. And I just created a function out of it. So I'll run the function. So I can give it the task ID and it'll see if it's completed and give me the results. Okay, let's go to the next one. So example 2 is the Toffoli gate. You can see there's a number of smaller gates that are needed to build the Toffoli gate. You start with the header mod on qubits. This is qubit 0, 1, 2. Header mod on qubit 2, that's this one. C naught between 1 and 2. A T gate or T inverse gate. So it's a rotation in the negative direction around the z-axis rather than a rotation in the positive direction on the z-axis. So that's a TI inverse 2 on qubit 2. Then there's a C naught from 0 to 2. Then the T gate. So you can basically see I'm step by step creating the Toffoli gate. So all of that was needed just for the Toffoli gate. And then you can print out the Toffoli gate. So there it is. I can run it on my simulator. Okay, so now what I'm doing here is, that's what the Toffoli gate looks like. And then I copied it into what I'm calling like the T10. Basically what I'm doing here is, I'm going to print this out. All right, so I'll show what that is. So if you notice, so what does the Toffoli gate do? It's got two controls and then the NOT, right? So if both of these are 1, then this will flip. 0 will become a 1. So if I give that a 1, this will still remain 0. This will still remain 0. If I give it a 1 over here, it'll be a 0, 1, 0. If I give it a 1 and a 1, right, 1 on both controls, then this will flip from 0 to 1. So 1, 1 should give it 1, 1, 1, 3 ones. So all I'm doing here is trying out, actually seeing what results I should get. So T10 is I put an X gate on the top to make the first control a 1. And so my result out of this should be basically 1 on the first qubit, still a 0 on the second, or Q1, and then the last one should still be a 0 because I don't have 1 on both the controls. So this should be, the answer should be a 1, 0, 0. All right, so that's my circuit. I'm going to run it. So I give it 1,000 shots. I get 100 as my output. Right? Any questions? Actually, I'm not looking at the. All right. So now I do the same thing. I do a T01, create a new circuit, T01. In this case, what I've done is I've put the X on the second qubit. Oh, should print it out. All right, so you see I've got the X on my second control. So the answer still should be 0, 1, 0. So I'll run it. I'm running that T01. All right, so my answer is 0, 1, 0 because I didn't have 1 on both controls. And now over here, I'm going to put 1 on both of them. And make sure I print it. All right. So now I put X's on the first two controls, which makes the 0 into a 1, right? So I've got 1 on both my controls, which means the C0 gate, if my circuit was correct, my answer should be 1, 1, 1, right? And so I'm going to run T11, and I get 1, 1, 1, 100% of the time. And this is on the simulator, so it should be great. You know, you get perfect results. So now what I do is I create a THH where I put header mods instead of putting the X gates that I was doing, I put Hadamards on my controls. So if you know what Hadamards do, they basically put you in superposition. They put that qubit in superposition of both 0 and 1, right? So print THH. So put these Hadamards over here. Now, if I run this circuit, what it's doing is it's going to basically run through all the 4 possibilities. The 0, 1, 1, 0, 0, 0, and 1, 1. And my answer should be all the 4 possible answers I should get. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, right? So now I'll run it. Oh, I guess I was just printing it. So here's THS, I'm gonna run it. So ideally, and it's easier to see it on a graph over here. So it's not very even, but, and again, this is on a simulator, but if I have enough of the shots, I should get equal, all the answers should be equal. The 1, 1, 1, 0, 1, 0, 1, 0, 0, and 0, 0, 0. Those are my 4 choice options. That's what's going to come out. And they should be equal probabilities. So what I did is, let's see. All right, so we're almost over time. This is my result. Okay, so we're going to switch gears a little bit. So yeah, I've kind of shown you the 2 circuits I'm dealing with. And now I just want to compare the results of the Bernstein-Vazirani between IBM and IonQ and the Toffoli gate between IBM and IonQ. All right, so that's what I'm going to do now. And again, you know, I had to submit the results. I had to wait a day for the results to come back. Even IBM is very busy these days. It took hours for the results to come back. So it's not practical or possible to show this in real time. But, you know, I submitted the job, then I got the task ID, you know, then I put it in the task ID to get the results. So here are the results from the Bernstein-Vazirani. In the Bernstein-Vazirani, as I had mentioned, IBM gives the 0011. And so 50% of the time only did it give me the correct result. And then you can see it gave me a bunch of other results from the IBM chip. And this is the result I got from IonQ. On the Bernstein-Vazirani, I paid 10 cents for it, plus 30, so they actually paid 40 cents for it. I should probably correct that. So this is 40 cents for this result. So I got the 1, 1. If you remember the Bernstein-Vazirani, I put the circuit where I had the control on the first 2, so I should get 1, 1. And I'm ignoring the last one. So from, this is not the simulator, this is from the IonQ device. I got 100% the correct result, because so ignoring the 1 and 0 over here. If I take all of my 10 results, they are all 1, 1, 0, 0. Absolutely clean. And compare that to this result over here. And here I did it 100. I think I had 100 trials over here. And then over here, I think I did 10 shots. I only did 10 shots. So pretty good results. Rigetti price is, I'll have to go back to that. Let's see, devices, Rigetti is 30 cents per task, and then It's much cheaper per shot. So you can do 1,000 and not bust your bank account. Okay, so that's the Bernstein-Vazirani results. You can see the IBM chip versus the IonQ, almost like perfect result. Then the Toffoli gate. For the Toffoli gate, I ran it on 2 devices, the IBM Athens, which is IBM Athens is a quantum volume of 32, which is supposed to be a better chip. You can see the results over here. Now this is the Toffoli gate. I'm using the Toffoli gate with the Hadamards. So I'm supposed to get four results. And you can see over here, it's hard to tell what result I really got. I got a 111, 29%. I got the 100, 18%, 010, 20%. I got 000, 20%. So these are the main results, 20, 22, 18, 29. And then I've got some extras that showed up. And that's on quantum volume of 32. Then on quantum volume of 16, which is the IBM RSense, which is slightly lower quality chip, I got 25%. This is not a valid result. 10, 30%. 100 only 10%. 111 only 22%. So I mean, if you didn't know the right answer, looking at this, it's hard to tell what the right answer is. And then from the IonQ, I did 100 shots. So I paid $1.30. And for 100 shots, I got these results. So you can see in this case, if you compare, slightly better, but I mean, it's still, so 00 was more than 30%, 100 around 25, 1010 around less than 25, 111 also less than 25, almost looking similar to this result. And then I've got a few of these other invalid answers. Not as bad as the I don't know, I would say it's a little cleaner, maybe a little better than those 2 chips, but there's not really a full benchmark, but you can kind of see it's slightly better results, not too many errors, but the values are still fluctuating quite a bit. They should have all been 25%. Okay, so that was my presentation for IonQ.
Thanks, Alex. Got a few questions for you.
Yeah, questions.
Why didn't you get the different answers equally for the Toffoli gates on the simulator?
Oh, why would they not equal on the simulator? That's a good question, like over here. So there are different kinds of simulators. You can have a state vector simulator, which is supposed to give you like the perfect result. It's the mathematical, you do linear algebra, it's the calculated results. And then you have results that come from a simulator where in certain simulators, and I do believe this is the same thing with the IBM simulator, the 30 or 31 qubit simulator, they introduce a little bit of error to make it look like, okay, you're kind of simulating a real system and you're going to get some erroneous values. So there's a little bit of error that they introduce into the simulators. Now, if you do a state vector simulator, you are getting, you get the perfect mathematical results, which is what I was getting when I did the, I wonder if I used a different one over here somewhere. There is a state, I think there's a state vector simulator in AWS Bracket. There's state vector simulator in the SDK for IBM Q. So if you use those, you get perfect results.
Do you have any idea what the, I guess, published quantum volume measure is for the IBM Q by chance?
Oh, I don't remember. I don't know if they ever published that. IBM believes in their quantum volume. I don't know if others believe in the IBM measure of quantum volume. So I don't know if we'll have to do a Google search to see if IonQ has published a quantum volume result.
I would think.
I would think it's somewhere around 32. I wouldn't think it's too much better than 32. I mean, 32 is a good quantum volume for these chips. And there's a delay on the IonQ side. So how do you measure the delay? The quantum volume isn't talking about the delay factor. So this is a slower, IonQ is a slower chip. It stays coherent longer, but the gates take longer to execute.
But they have better fidelity, right? I believe,
they have better,
right? Because
slightly better fidelity and fully connected.
It's at the atom level, so you should be getting much better error, much less error, as you indicated on the IonQ machine.
Yep.
Than the IBM.
Error, but as you can see, it's not. I mean, it's not perfect.
It's not zero. No.
Not zero. I mean, this is why so much research is going into error correction.
Yeah. Well, I think the community has kind of come to terms with errors. In this business, there will always be some degree of error. But am I correct? Am I accurate in saying, Alex, and I'm not a hardware guy, but the IonQ, because it is using atoms, should be less error prone, not zero, than you know, the IBM approach. Wouldn't that be true?
I mean, you know, if you look
fidelity
at the
would be better.
Picture behind me, right? This is kind of like a representation of what an ion trap would look like. The ions are in a linear, you know, they're in a straight line, and they're given laser pulses, and when they're a 1, they actually light up. So every dot is in this picture, if you imagine it, and if you imagine these are different instances, you know, different examples of an ion trap with ions lit up. Zeros, where you don't see them, it's a 0. Where you see them, it's a 1. And they're shining lasers, you know, they've got one laser, then beam splitters, and then they're doing all kinds of controls and ensuring that lasers hit the ions from both sides and move the ions in that magnetic field. And then when it relaxes, you know, it starts shining. I mean, we're controlling atoms. I don't think people realize that how small they are and that you have to have these perfect beams with the right frequencies hitting them in the right way for the right amount of time to be able to do what we just saw. I mean, it's just absolutely mind-boggling, I think. This is fascinating that we can even control these ions and not lose their energy, or they don't decay, or they don't, you know, jump down, or they're not affected by some of the magnetic field or from the environment. I mean, this is extraordinary where we're at right now.
The IBM machine, I'm asking because this is not my space, but for conversation's sakes, the IBM machine is using electrons.
No,
right?
IBM is using superconducting qubits. And what that is basically a loop of current.
Okay.
Which is generating a magnetic field either in the up direction or the down direction within the superconducting squid circuit, or you know, there's a Josephson junction on 2 sides or 1 side, and then loop. And so it's a superconducting circuit or a superconducting loop, which allows the current to flow without any resistance and creates, a magnetic field either going upwards or downwards, depending on whether it's rotating clockwise or anti-clockwise. So, I mean, that has its own control issues and its own issues of, getting it up to one energy level and controlling the gates. There are errors there. You're dealing with, you've got basically a chip that's on a substrate, which is getting heat or energy from the environment that comes right onto the chip itself and right onto that circuit. So you have to shield it from magnetic fields and error, heat, and all of that stuff. Here you've got these ions basically suspended in a vacuum within a magnetic field, and you have to shield them from all the magnetic field, noise, cosmic radiation, whatever, to stay coherent. So, each one has its own control issues. Each one has its decay, where the state will come down to the lowest state. And so, I mean, each one has its own challenges.
Alex, got a question from Konstantinos, and actually I'm pondering this myself, actually. How can you understand that decoherence has taken place?
So is it a wrong result or is it decoherence? So, so from the simulator and from math, we know what the right result is, right? So we know what the right result is. Now the question is, did I get the wrong results because something else is going on in the circuit versus decoherence? Is that what you're asking?
I'm going to guess that, if your phenomena decohere, what happens? So, if you're somehow able to run a long time.
So there's many reasons why you can get wrong results. When I was actually applying the rotations in the Toffoli, right? When let's say for the Toffoli gate, it's laser beams are hitting the ions and moving them up to certain levels. Your control system could be inaccurate or not calibrated, so it never really got to where it needed to get to, right? My gates just might not be very good, right? My gate operations might not be very good, so they don't allow the qubit to reach the state it's supposed to reach. So that could be happening. My gates could be perfect and it reached the right level, but by the time I did the measurements, it started to decohere. And so different qubits started relaxing. And so they were not at the spot that they were supposed to be. The one became a 0, right? So here, instead of, I've got a 1, 1, 0. Where did the 1 come from, right? This should either have been a 1, 0, 0 or a 0, 0, 0. So somehow something that was supposed to be a 0 became a 1. Generally things go from that at the high energy level go down to the lower energy level, right? So this could be, for example, I had a 1, 1, 1 where the 1 became a 0. I lost my 1, right? This could have been a 1, 1, 1, and I lost my middle one, became a 0. So generally you go from higher energy to lower energy. So these errors show up, they're showing up because my qubit wasn't at the energy it was supposed to be at. So it could be my control system never got it to the right state. My gate operations, by the time I did all my gate operations, I started losing coherence on all the qubits. The amount of time this gate operation took, with all of the different calculations it had to do, which is a reasonable amount, I could have started losing coherence. So I might be doing these gate operations, but I'm doing them on the wrong state. I'm not retaining the perfect state along here. by the time I get to this operation, I've already started losing information. My zero, ones have become zeros, or they started, I'm doing rotations over here. So a rotation about the z-axis can also decay and start kind of wobbling, or, um, just kind of meandering over to the wrong side. So when I do another rotation, I'm doing it starting with the wrong place. And by the time I do my final operation, I don't get the right result because things have been basically decohering or not being controlled properly. There's many, many reasons for the errors. And so this is why the field of error correction delves into, ensuring that the gates did their job, ensuring that the qubits retain. If they start losing, then there are some gate operations to get them back to where they should be. That the control systems to make sure the qubits stay in the state that they're supposed to be for whatever the length of the quantum circuit is. Let's say it's like 1 microsecond. It needs to be able to retain that. And if we're going to do any sophisticated calculations with these, at some point we'll probably be running circuits for, milliseconds. We need these qubits to retain that or millions of qubits to retain that coherence for milliseconds. So that's going to be it's going to be a while before we can get it to that point.
Yeah, I'm thinking about that. I haven't seen, I'm not saying it's not there, but I haven't seen like where the control in Qiskit, for example, and again, I'm not saying it's not there, I don't recall seeing it, is where the control system says, okay, I'm having a problem and I'm going to send an exception up to the higher level of the stack where you can say, okay, my qubits decohered, so I'm just going to abort.
Yeah, there's a whole library. There's a whole library for error correction. Q control, Q control, the company Q control has a whole set of mechanisms for error correction. And I believe IBM is probably using some of those mechanisms where it might be happening internally, right? You shouldn't have to worry about the error correction, right? Within the processing of the gates, they are doing the error corrections as well. If they were doing no error correction, we probably get worse results.
Well, error notification, so exception handling. So I would imagine, if not there now, eventually there'll be where you, at our level, at this level, at the Python level, think of it as where you can set, okay, I have a tolerance of this much problem at the machine level. And so if the control code reaches a threshold, send me an exception to abort, and I'll take some action there.
Yep.
So I'm talking above the level, I think, where you're talking there.
You're right. I think at some point they need to have some way of saying I'm beyond my tolerance.
Yeah.
My error tolerance, and that result is useless. I shouldn't have to pay for a bad result. I shouldn't have to pay the $10.
Yeah, in dollars and cents terms. So I'd imagine that's out there.
It's going to go back and give me a better result.
There has to be some mechanism, to alert you as the consumer of the device that a low-level error has occurred.
Yeah, so Tomas is saying you may simulate the errors and judge. So you mean like use a simulator and then compare? That's what we're doing right now in the NISQ era, right? And we're dealing with just a few qubits. But think about one day when you're using 30 qubits or more, there will be no way to simulate and know what the right answer is. And by then, we have to have confidence that the results that are coming back So if I see a result like this, how do I know if that is the right result if I don't have the confidence? Because, even the simulators, I think 30 to 34 is our maximum simulator. Very soon, you will not be able to have a simulator that can actually tell you what the result of your circuit would be. You need, like a supercomputer, or one day even the supercomputers will not be able to give you a result for some sophisticated circuit that you built with, say, 100 qubits. How would you know what the right result is if you can't rely on the quality of the qubits and the gate operations?
Okay.
All right. With that note.
Speaking of error modes, we're about to have a time exception going on here. Not that that's a problem. We can catch that and continue. Any other questions or comments from anybody before we give a warm welcome or warm thank you to Alex for taking the time to do this and all the energy?
I'll just copy paste this. This is where I've got the.
Oh, I put that in early on, Alex.
Okay.
So we got it. We got it on the record. Yep.
Yep. So you should be able to just download from here, get a zip file or fork or do it.
Also, for what it's worth, I threw in a little Python there if you want to pop that in there and to remove the ancilla qubit out of your printing, if you'd like. I've been coding Python for the past 3 or 4 days.
All
so
right.
I got it on my mind. You got to debug it though, no guarantees. But anyway, okay, everybody, good to see you all again. Alex, good to welcome you today. Thank you again very much for all the work that you put into this.
You're welcome.
On behalf of the team, the ecosystem here. So I think there's a lot to this, and if we each take some time to chip away at one aspect of it.
Yeah, definitely. I mean, the more we pay companies like IonQ and do these tests, the more they will improve the hardware, right? I mean, this is, it's like VR development or game development or GPU development. The more people that use it and pay the 10 cents, hopefully the better these devices will become, right?
Now, not that we're complaining to pay 10 cents to use a gosh darn quantum computer. We're spoiled nowadays, huh? Mm-hmm. Anyway, okay. Last call. Anybody? All right, Konstantinos, everybody, Barry, et cetera, Alex, thank you very much.
Yes,
we'll see you around then.
I think Konstantino wants to say something.
Oh, saying something. Okay.
Very, very, very quickly, my apologies. So I was going to ask you about a problem that I'm facing, and I'm sorry that I do it now, but I'm a hobbyist, so I have no network. So my question is, in order to prepare a normal array, a Python array, into a quantum superposition state, the way that I've done it, but I haven't seen it online, it's by using DFT and by adding some ones into the diagonals where there are no other numbers. So my question is there any framework for translating arrays to quantum arrays, to quantum superposition states?
That is I don't know if I have the answer for that right now. I'm assuming that you have a state that you're representing in a matrix, and you want the quantum computer to represent that state, right?
Yeah, let's say one dimension like array. Yeah.
Yeah. I mean, in the end, it is, as we know, quantum computing is really linear algebra, right? So if you are in Qiskit, I'm forgetting where I've seen this, but in Qiskit there is and I don't remember what it's called, but you can actually get the value of the matrix from your circuit. So yeah. I don't know if that's something you want to try. Try to do a search for a matrix visualization or linear algebra visualization. I don't. There's some visualization where you can get the value of your matrix from the circuit. Now, there are tools out there that will take a matrix and give you the equivalent quantum circuit for those.
All right. Yes.
So I don't know what if that's what you're trying to do, is like you've got a matrix that you want to simulate and you need the circuit to get to that.
Yeah, I was trying to create the Grover's the variation of Grover's algorithm to find the minimum of an array. And if you want to use Grover's algorithm, the typical scenario is where you have Hadamard matrices, and then you have all the possible states. But if I want to represent an array, I want some states to not be there. So the only way to do it is by preparing the quantum state. I managed to do it classically, but if you have like 10 qubits, for example, you need 2 to the n, 2 to the 10th. So like after some points, the matrix in my memory becomes so big. So I was wondering if there is any framework that translates directly the gates. Because what I do is I use the Rigetti emulator and I do it with linear algebra, and this translates it into a circuit. But I want to avoid this translation because this is what kills my memory.
Yeah, so I don't have an answer for that.
Okay.
Sorry, but connect with me on LinkedIn, and we'll see if we can kind of look around and see if we can find some solution.
Thank you very much. There is no reason actually. I do it just for personal reasons, but thank you very much.
I think that's
good.
That's a good reason.
And have you tried throwing these questions out in Slack Exchange or on Qiskit Slack? There's a lot of people.
Yes, you're right. Recently, I joined those those Slack networks and stuff. Yeah, let's say that it's not that I don't have the time. I want to be more prepared. I want to understand more the quantum thing before I go to ask those kinds.
No, you should ask. I mean,
Yeah.
no, I don't. There are, I think on Slack Exchange, there are probably the right people who, the PhDs that have seen these tools or use these tools, or on Qiskit, the Slack channel for Qiskit. You should definitely ask, because I mean, people are asking all levels of questions, how do I get into IBM Q, right? So, I mean, you shouldn't worry about that. You should just ask the question.
I don't think the culture here has gotten to the point where, what is it called? Flaming?
Yeah.
I mean, whatever it's called. I don't think quantum's at that point yet. So ask, dude. Somebody will pick it up.
And that's a high level, like tough level question.
Cool.
Thank you.
Well, good to see you then, Konstantinos. Okay, everybody. Again, Alex, thanks a lot. Have a great weekend. It might be sunny down there in Baltimore today. It is up here in Harrisburg. Not that we ever get out to see the sun anymore.
We have to get through the week before.
Yeah. Anyway, thanks again for the time, man.
All
It takes
right.
a lot of time and energy to do this. So we appreciate it. All right, everybody. Good to see you all, and we'll see you next time.